Write amplification can be a balancing act. The improper use case, along with data and system integrity operations, can increase the write amplification. Balancing all of that at the file system level can still leave the lower flash media level unbalanced. Databases have their own internal mechanisms that can unbalance the system. Increasing the size of the flash, a common solution, means everything must be rebalanced again. And with that bigger size, more items can show up to change the equation. And we haven't even factored in the added cost of larger media. Today, we're going to talk about what write amplification is and why it's important, the limited lifetime of NAND flash media. We'll examine how the file system and application work with or against the use case. Next is a look at NAND media write amplification, a peek beneath the hood from our team of NAND experts. And finally, my colleague Sami will talk about the test results we have on Linux and FreeRTOS. Write amplification factor is really pretty simple math. It describes the amount of data written to the media instead of what was planned by the user or the application. A write of 1,024 bytes that ends up emitting 1,536 bytes to the media would result in a write amplification factor of 1.5. Actual factor is highly dependent on the use case, and this would be averaged over the entire system. The write amplification factor is an important component of understanding the actual lifetime of the product design. This has been in the news recently, as products have delivered a shorter lifetime than expected, some leading to product recalls. These design challenges directly result from choice of media. NAND-based media includes SSDs, embedded storage like eMMC and UFS, SD cards, and other types of removable storage. What makes write amplification factor so important to understand on NAND-based media is that it has a limited lifetime. This is measured in program and erase cycles and depends on the type of underlying NAND used. In larger write amplification factor results in more programs and erases and less lifetime overall. Another important factor of NAND is copy on write, and we'll talk more about that shortly. One frequently proposed solution to the shrinking lifetime is to use larger media, but that doesn't always solve the problem, and we'll discuss that too. Also, larger media costs more in designs. The use case for a design is directly related to the write amplification factor, but the system designer is not always able to define that use case. A single-threaded system that directly logs data to NAND flash write pages could be designed to use writes that exactly match the write pages. It would have a write amplification factor of 1.0. Adding in a file system and multiple threads and overhead for system and data integrity necessarily increase that factor. From the other perspective, we could talk about worst case simulation, writing a single byte to the file system file and then flushing and syncing that data for a write amplification factor of more than 1,000. We don't really plan to examine that perverse case further, but understanding why it creates such a penalty on the media can be useful. These are really big numbers, and most people who glance at write amplification are expecting small numbers, usually less than 10. A paper by Hyojun Kim and NEC Laboratories found a write amplification factor of nearly 20 in 2004. In a related interview, the author said, apart from the benefits of selecting a good flash card, there are some fundamental ways we're using storage in a bad way. In a 2019 paper, a research team was easily able to provoke a write amplification factor of 80, and we've seen similar results from our customers. So what sorts of numbers have we seen? Well, the specifics are in our testing section. But the common use cases on Linux, such as growing log files and adding small updates to SQLite databases, have shown a wide range of write amplification, from 2 all the way up to 650. The use case really, really matters. The easiest and most obvious overhead comes from the file system. Scaling up the writes, as seen here, is going to be dependent on the use case. The file metadata contains important file information, including the name, the date, the time, the size, and any attributes or flags. Folders and subfolders also contain their own metadata with similar entries. On FAT, the FAT file system, the metadata entries take between 32 and 128 bytes, both of which are far less than one file system block. And for a small file, this ends up doubling the amount of data stored with a write amplification factor of 2. But for files in the multiple megabyte size range, this really ends up being a very small factor. Another place that the use case matters is how that data is written. For a file where log data is streamed continuously, the file system can be set to flush in even block increments, and that minimizes the overhead. NAND media does not allow you to overwrite things. Instead, a copy is made, which also contains the new information. This is known as copy on write. When the files are updated, in the middle, there are often partial blocks at the beginning and end of the modification, and this increases the write amplification. In systems with multiple write threads, the interleave of data can also up the write amplification. Linear data means less frequent updates to the metadata. Fragmented data leads to more extents and more frequent metadata updates and larger write amplification factor. Data that is frequently flushed to the media improves the data integrity. But whenever those updates are less than a file system block, this use case will also increase the write amplification factor. Don't forget that each of these is also an update to the metadata and its write amplification. Various system integrity schemes, the reliability of a system, can increase the write amplification factor as well. Linux ext4 uses a journal for the metadata and any optionally data as well. The rights to the journal duplicate the rights to the rest of the media, and each of these rights increases write amplification factor. Other file systems use different methods to ensure system and data integrity, and all of them increase the write amplification factor by some amount. Let's come back to the storage. Most of the write amplification being done by the storage is invisible to the file system, the application, and the system user. The effect can eventually be seen in reduced lifetime and limits to performance and throughput. We talked earlier about the write page and how writes are scaled up to match that. Packaged media vendors from SD and SSD, and that includes eMMC and UFS, provide caches and buffers internal to those packages, and that reduces the impact of these small writes. They're usually collected until an entire write page is ready to be written. This is an excellent strategy up to the point of requiring a write to be on the media for reliability, data, or system integrity, which we just covered. Each erase block on the NAND media is made up of several write pages. The exact number depends on the media configuration. Another type of amplification at the media level is known as erase amplification. In short, as the write pages within an erase block are used, that block ends up being fully programmed. Since overwrite's not possible, each write page that's been replaced is marked as being obsolete. When the entire erase block is full of obsolete data, it can be erased, which provides several new pages ready for data. When the system needs an empty erase block sooner than that, it performs what's known as compaction or garbage collection. The remaining write pages with good data are written to other locations on the media, and that results in a block that's ready to be erased. All the blocks are obsolete. This phenomenon is known as erase amplification factor, or EAF, and these extra writes were not factored into the earlier calculations. Usually this is invisible outside the media layer, but it definitely counts against the budget of program and erase cycles, which is, remember, quite limited. Use cases with mostly full media are especially prone to this additional hidden erase amplification. This is why it's important that the file system informs the NAND about the deleted data. To allow for this, storage interfaces designed for NAND media add a discard, which is also known as trim or erase command, in addition to read and write commands of traditional rotating hard drives. We've seen the impact of the application already, though partial and small writes and updates and frequent flushes and syncs. Applications which tread lightly on the file system will create less write amplification factor for the overall design. Not all applications are under the designer's control. In a recent problem case, the system utilized several components which were very helpfully generating log files and tracking their usage. Unfortunately, each of these additional writes, many in multiple threads, were causing a huge write amplification factor challenge for the overall design. One situation the designer has little control over is database usage. Databases can be the worst offenders for increasing the write amplification factor. They make small writes, many and updates in multiple locations, and require frequent sync or flush operations to provide their data integrity. And of course, attach additional metadata or keys to each of the stored user data. The Android SDK has built-in support for SQLite, and that's often used by applications to store structured data used and collected by applications. While using database is efficient for an application, it can create challenges for the flash media. In the test results section, we'll discuss in further detail how the databases handle small updates to SQLite database and why they lead to a high write amplification factor. When we talk to our customers, we find they've recently spoken with flash media vendors who give them a number like 1 million write cycles. Without context, that phrase just does not provide enough information for how the media will deal with customer use cases. How can this be translated into an expected lifetime? The automotive community and SSD vendors both measure storage in a measurement known as terabytes written, or TBW. This is defined by the standards group JEDEC as the number of terabytes that may be written to the media over its lifetime. This is JEDEC standard JESD 218. Factoring in the information mentioned earlier, both the write amplification factor and the write volume workload, they can define a requirement for a design. When problems occurred, one recent automaker's design replaced an 8 gigabyte eMMC with a 64 gigabyte part, theoretically resulting in 8 times as much life and 8 times larger TBW. This can go some distance towards repairing situations where the workload is greater than planned. For instance, more frequent security updates and increased sensor logging. Increasing the media size scales or changes all of the calculations that we've been talking about, though, for write amplification factor. Besides the increased cost of that larger part, larger media tends to have a larger write page size. File system block sizes can also expand on larger media, though Linux file systems are often limited to a maximum of a 4K block size. All the previous write amplification factor calculations have to be redone for the larger media, and the write amplification factor often grows considerably. The metadata didn't grow, the size of the part did. Teams which find they have additional space available may add to the amount of data logging they perform. As desktop hard drives and memory capacities have grown, desktop operating systems and applications have never gotten smaller or written less data.
To illustrate how write amplification is affected by the use case in a file system, we ran a selection of test cases with different configurations to simulate 2 common use cases: growing log file and a growing SQLite database. We focused the testing on a Linux operating system due to its prevalence in embedded systems, and we tested the write amplification using a Renesas RCAR M3 starter kit with a 32 gigabit eMMC and on a Linux 5.4 kernel. And we wanted to showcase the differences on write amplification and erase amplification. We run the same test cases on 3 different file systems that are available for Linux. X4, that's provided within the kernel, Tuxera's Reliance Velocity, and Reliance Nitro. We selected those file systems due to their different measures for reliability. X4 is a journaling file system, while Reliance Nitro is a transactional copy and write file system, and Velocity does prioritized write operations to provide system integrity. So here we have results from our growing log file test case. We tested different sync frequencies after every append to the file, after 16 appends and 128 appends. We tested this to showcase the differences between how you can help write amplification by combining writes to a bigger write at the same time that's committed to the media. And we also tested that with 3 different file systems, and we can see significant differences over the reliability methods. So overall, X4 has roughly double the size of the write amplification due to its journaling. As Thom said previously, journaling always increases the data write amplification by a factor of 2, as we can see in the results here. Now, once we are committing more data at once to the media with 16 or 128 operations in between, we can see that the write amplification as well as erase amplification are significantly reduced in this use case. Then we come into the interesting part, which is the growing SQLite database. Now, we tested growing SQLite in 4 different ways. We tested in the default way, in a write-ahead logging mode, and we tested it with 4 processes and 1 process each. And as Thom was discussing earlier, databases do small updates to different locations when they are updating the data. And as we can see here, the write amplification is significantly higher with an SQLite database than it was in comparison to a growing file. Here we can see that the smallest write amplification is around 128, which is significantly larger than on a growing file. Here as well, the X4 with its journaling method increases the write amplification, while Reliance Nitro and Reliance Velocity has a stable write amplification all over the testing. So, based on the test results we showed, the smaller the amount that's written between the syncs, the higher the write amplification factor. This is due to the file system often having to write the minimum of 4K block sizes, and when we increase the sync interval, multiple write requests get merged into one in the Linux caches, and that leads to a smaller write amplification. That's due to, instead of multiple small writes each, caching leads to having only one write associated with the data. However, decreasing the syncs has implications on data integrity. Having longer sync between the commits means that the data is not written to the media immediately. And this can be a concern in an embedded system where power interruptions can occur at any time. Importantly, data reliability method of the file system chosen has a big impact to determine how to best keep the data safe. While non-journaling file systems only write the changes once, journaling file systems keep the overhead, or has additional overhead due to the additional journal file. And this difference is significant, especially when the writes are very small. Compared to a growing log file, SQLite workload with the same size writes has significantly higher write amplification. The differences in write amplification factor between updating the files and the SQLite database is due to how the SQLite database works by having multiple writes associated with each insert, what is considered as an individual transaction for data integrity on the SQLite database. By treating each of the inserts as its own transaction, SQLite is trying to ensure that the database is always up to date and that there's no stale data, but this leads into a higher write amplification factor. Now, SQLite creates a journal file for each of the transactions and deletes it once it's merged, and syncs the data in between to the media. In addition to writing and multiplying on the application level, the metadata updates of the file system generate additional updates. What we saw in the past, or in the previous slide, on write-ahead logging mode, the changes are written to a separate file first, and the file can store multiple database operations, which help to reduce write amplification. As the SQLite documentation mentions, the disadvantages of a write-ahead logging mode is that it's slower for reads since the entire write amplification. As SQLite documentation mentions, the disadvantages of this mode is slower reads, since the entire write-ahead logging file must be processed to find out the current state of the database.
Today, and in the accompanying white paper, we've defined what write amplification is and why it's crucial to understand it for NAND flash-based media. We showed the impact of file systems and applications and the hidden impact of erase amplification. With a greater understanding of these limitations, the development team can work to reduce the write amplification factor and extend the lifetime of their embedded designs. We also shared some of our test results that we've seen and would be happy to discuss these further with your team. All the measurements we performed can be factored into your use case, leading you to better predict the impact on the lifetime of your design, even avoiding product recalls. At Tuxera, we believe in the success of developer projects and the happiness of your customers.